Hello, classmates. I have selected depth first search as my algorithm to demonstrate. In order to show depth first search, I also have to show breadth first search because that's the alternative when searching in binary trees. If you did the search project, you would have done both depth first search and breadth first search with a graph. The terms depth and breadth don't have a lot of meaning in a graph because they don't really have an up and a down or a left and a right per se. But in a binary tree, they do. And I believe that this is really the origin of where the term depth first and breadth first comes from, is when searching in a tree. Specifically for my demonstration here, I'll be using a binary tree. A binary tree, like all trees, has a single root node. As opposed to a graph, which can have multiple entry points. It has a single root node, and that root node can have, each node can have no more than two child nodes. That's the reason for it being called binary. So there are two different search algorithms I'll be talking about for binary trees. The first one is breadth first, and you can see a lot better where that name comes from. We're going to search the breadth or the width of the tree before we search the depth of the tree. In a breadth first search, we first start on the left node of the root node, in this case B in the tree I'm showing here, and then we proceed across every node in that same level. So before we proceed down to the third level, if the root node is the first level, we go to the second level, we then visit every node, we then go to the third level, visit every node, and then go to the fourth level and visit every node. So we've visited the breadth of the tree before we visit the depth of the tree. A depth first search, of course, is the opposite. So we're going to visit all the way down to the bottom of one branch, then we'll backtrack back up again, and then we'll visit to the bottom of that branch, so on and so forth. In a depth first search, we do in a depth first search, we do start on the left-hand side by convention, as far as I know. So we'll basically just continue down the left side from the root node. We'll continue down the left side of every node until we reach the bottom. We then backtrack back up again. So in this case, we go A, B, D, H. Once we've reached H, we've searched every part of the B node. The D node, of course, having only one child, we've completed its search just by hitting H. We then go back up to B, we go to E, then we visit the left node of E, we go to I, then we go to J. At that point, we've searched all of the children of the left-hand side of the root node, so we proceed to the right-hand side and we do the same algorithm over again. We go to the right node, then its left node. F has no left node, so we go to its right node, then we track back up again, and finally we go to G. There's a difference, of course, between searching and traversal. Traversal of a tree is where we're going to visit every single node. In a search, we're going to search every node until we find a particular target node. So let's talk about the the example code that I'll be giving you and the exercise that I'd like you to do. So I'll be giving you two trees, and there'll be three different use cases for those trees. So we have a smaller tree. I like this one. It's nice and simple. And then we'll expand this tree to make it a larger tree with a few more cases that might hang you up. So in this tree, we're going to be searching for the C node. And so again, we're going to start at A. We're going to choose the left-hand node. From there, we're going to choose the left-hand node again, which brings us to D. We have now reached a leaf node, which a leaf node is a node that has no children. So we go back up to B, and then again we go to E. From there, we go back up to A, and then finally we have found C. That means that the path, and what I'm going to be expecting your function to return in my exercises, is A, B, D, E, C. We, of course, don't visit F because once we visit C, we stop because it's a search. If it was a traversal, we would continue on to F, and then the traversal would be done. So let's expand that tree a little bit. So here I've taken the same base tree, A, D, A, B, D, E, C, and I've added some more nodes to it. So now we go down all the way to G. So in this search, we'll be searching for C again, but we're going to have some extra steps. So we're going to go from A to B, B to D, following down the left, and then G. And then finally, we finish up with G. So we go back to B, go to its right node, which is E. That finishes up the whole left-hand side of the root node. And so now we go to the right-hand side, we go to C. And so, of course, our path is very similar to the last one, but we've added G. Now, in the last step, I'm going to have you use the same tree, but you're going to traverse the entire tree. So the traversal to C remains the same, of course. And then once we hit C, it has no left node. So we go to F, which is the part that may catch you up, is that if you haven't written the code correctly, you'll be looking for a left node, you won't see it, and your code may stop. So instead, because there's no left node, we go to the right node, which is F, we go to its left node, which is H, and then finally we end up at I, which is our target. So we finished both the traversal and the search, finding I. And that gives us the path here. These I'm going to include this PowerPoint because the tree visualizations here and the answer paths are important because we'll be using these trees in the exercise. Lastly, that first image I showed you I got from here, so I've included that in my references. All right, let's talk code. So I've uploaded 3 files. One of the reasons why I really, really like binary trees is because they are extraordinarily simple, and the code that goes with them can be very simple. We can, of course, you can add weights, and just like a graph, you can make it rather complicated. But in this case, I've like to keep it very clean and small. So I've created a node class, and so this class, every single node in our tree will be represented by a copy of this node class. It only has 3 properties. It has a name, it has a left node, and a right node. These are defaulted in the init function to none, so you can either pass in left or right or neither. Let's look at the example code that I've given you. So I've attached 2 files. There's the example code and the example code with the solution where I provide my solution to this function. You will be doing all of your coding in this DFS function. I've given you a little description here to remind you what to do. And I'll also be walking through the solution here in a couple of minutes. So in your DFS function, you'll be passed in a root node, or if you're solving this recursively, it will be a sub part of the tree, and we'll talk about that when I go over the solution. And then a target node, so the node that you're looking for. This is just passed in as a string. And then what you're expected to return is a list containing single characters. It would look like this, for example, that contains the path starting at the root node, ending at the target node. You should be including both the target node and the root node, as you can see here in the first answer. So the other thing I want to go over really quick, just in case you're curious, again, there's no need for you to go through the tests or even read them if you don't want to, but I do want to show how I build the tree, the 2 trees, because I do build them differently. So let's look at, let's look back at that simple tree. So again, it's got just these, it's got A has 2 children, B has 2 children, D and E, and then we have C and F. So in the first example, I build the tree from the top down. So I build A first with 2 empty children. Then I build B with 2 empty children. I then set D and E, and then I come back up again and I do C and F. Again, this isn't, I just happen to be building it in the same way we search it, but that's a coincidence. You could build it in whatever order you want. So here I create the A node, which I'm going to reference as the root node inside my testing code. Then its left node, I create a B node that has no left and right. I create a C node that has no left and right. And then I simply can do root.left, which is B, and then dot left, so the dot left of my left, which is B, becomes D. D, of course, I don't need to provide any children because it is a leaf node. Same thing with E. So D and E I just add. And then finally F I just add. And then finally C and F I add here and here. All right. The other way to build the larger tree, I build it from the ground. I build it from the bottom up. So if we look at the larger tree, I'm going to start at the bottom most nodes, and I'm going to build them up. So I'm going to first build G. I'm going to first build G, and then I'm going to make that and then I'm going to build D. And since I've already built G, I can assign D's left when I do that, so on and so forth, building it up. So here, for example, you see, again, the initialization function takes 3 parameters, the name, the left, and the right. If I'm passing in just one left or right node, I like to use this more explicit syntax of left equals or right equals. Here I could also say left equals D, right equals E, but that seems a little redundant. So I build the G node. The D node then only needs the G node. The E node then needs both the D. The E node, of course, then is the other leaf. So B uses D and E, so on and so forth. And I build the tree up from the bottom. And that is it for your assignment. So if you would like to take a shot at this, go ahead and pause the video here because next I'll be covering the solution. All right, let's move on to the solution. So I'm not going to cover the testing code again because I've already covered that previously. Let's just look at how I solved this problem. Uh, Tree traversal can be solved iteratively or recursively. It's traditional to do it recursively because, as you can see here, the code is actually really, really simple, although it can be a little hard to understand. So I certainly encourage you to take a shot at it, even if you've taken a look at the solution, or maybe even try it iteratively. So in any recursive function, you have to have at least one base case. That means a situation where a parameter passed in will result in you not making a recursive call. So my recursive calls here, I'll point them out now, are here and here because I have to make a recursive call for both the left and the right nodes. But I need to have at least one base case. So in my case, I make the recursive call even if the left or right node is not set. As you can see in my class here, I'm defaulting them to none, which is basically the Python null type. So if the node passed in is null or none, I simply return an extra empty list. As you can see down here, I'm appending the list to my path as I build it, so this won't affect my path that I'm building by passing an empty list. And then, so once I've dealt with that base case, then I have the other base case, which is if it's a leaf node. So if its left and right nodes are equal, which means that they both equal none, because that's the only way that they could be equal, then I simply return the path that I've started building. So I start building the path with the current node. Again, assuming my code kind of assumes that we're at a leaf node. So because we have to visit that node, I add its name to the path. And then uh, if that's a leaf node, I simply return that path containing its name, which in the recursive calls gets appended to the path I'm building. So let's say that this was the A node. I would set the path equal to a list that has a value of A. I would skip this because it has two different nodes. If you'll recall here, it has a B node and a C node. So then what I do is now I do the recursive call. So first I visit the left node recursively and I visit the right node recursively. Now because this is a search, I have an extra step in here. So if I visit the left node, I may or may not visit the right node if I have found my target node. So if my target node is now included in my path, so if C is at the end of my path, then I simply return the path and then that populates back up because it's recursive. That ends the chain of recursive calls. If I'm continuing the search, then it would continue to the right node. I don't need to check to see if the right node is in the path because I always return the path at this point, so an if here would be redundant. And that's my entire solution. So I hope you take a shot at it and let me know if you have any questions or comments. Thank you very much.